Hi guys, welcome back. This is Vanajakshi, pursuing my education at Sri Venkateswara College of Engineering and wearing the SN 1V21 CS 184. I am here with the topic Spectral Clustering with Linear Embedding, a discrete clustering method for a large scale data. Introduction to spectral clustering. Spectral clustering is a powerful technique for grouping similar data points based on their features. It leverages the elevations of similarity matrix to identify the clusters. This method is particularly effective for non-convex shapes and complex data distributions. The spectral clustering is a variant of the clustering algorithm that uses the connectivity between the data points to form a clustering. It uses the elevations, that is values and vectors of the data matrix to forecast the data into a lower dimensional space to cluster the data points. It is based on the idea of a graph representation of a data where the data points are represented as the nodes and the similarity between the data points are represented by edges. The steps performed for the structural clustering are build a similar graph of the data. The step builds the similarity graph in the form of adjacent matrix which is represented by A. The adjacency of matrix can be built in the following manners: epsilon neighbors, k nearest neighbor algorithms, fully connected graphs, direct an edge from U to V and V to U among the k nearest algorithm, direct an edge from U to V and from V to U if neither V is among the k nearest or U is among the k nearest neighbors of the V. Fully connected graph. To build this graph, each point is connected with the undirected edge by the distance between the 2 points to every other point. Since this approach is used to model the local neighbor relationships, thus typically the Gaussian similarity matrix is used to calculate the distance. Basics of linear embedding. Linear embedding transforms the data into lower dimensional space while maintaining the relationships. Techniques like principal component analysis (PCA) are commonly used for this purpose. Reducing the dimensional helps to improve the componential efficiency in clustering of the algorithm. Similarity matrix construction. The first step in the spectral clustering is constructing a similarity matrix from a data. This matrix quantifies the similarity or a distance between the pairs of the data points. Common methods for constructing these matrix includes k-nearest algorithm and the Gaussian kernels. The k-nearest algorithms or is an algorithm as you can see in the figure on the right side, the spectral clustering, the first k eigenvectors use a new clustering space. We have u1 and u2 where 1 0 1 0 1 0 0 1 and 0 1. There are the y values where y1 y2 y3 y4 and y5. We use a clear clustering algorithm for the new space. You can also see the similarity graphs. There is 1 is connected to 2 is connected to 3 and 3 is connected again to 1 and 4 is connected to 5 and 5 is connected to 4. Eigenvalue decomposition. Once the similarity matrix is constructed, eigenvalue decomposition is performed. This process identifies the eigenvectors that represents the structure of the data and the leading eigenvectors corresponds to the most significant dimensions for the clustering of an algorithm. Clustering of embedded space. After obtaining the eigenvectors, data points are projected into the lower dimensional space. The clustering of algorithms like the k-means are then applied in the new space. This step enables the identification of discrete structures which are most effective and efficient. You can see in the image before the k-mean algorithm, you have all the dots at the same space which always look the similar. After the k-means, you can see that blue are separated to one side and red are separated to one side. This is nothing but the clustering in an embedded space. The space is been created between the one category and the other category. Advantages of a spectral clustering. These spectral clustering can capture the complex relationship between the data points that other methods may miss. It is less sensitive to noise and outliers the compare traditional to the clustering algorithms. And it also has the ability to work with the non-linearly separable data that makes it as an high versatility. Challenges in large scale data: conceptual cost can be significant barrier when dealing with the very large data sets. Memory constraints may limit the size of a similarity matrix that can be constructed. Efficient algorithms and the approximations are essential to make the spectral clustering feasible. You can watch the big data challenges over the image. The big data challenges include poor data quantity, issues for scaling, incorrect integration, real time of the data, lack of expertise, security and privacy, originalization, realistic, data verification, heavy expenses, wide technology variety. Recent developments and approaches: novel technologies like approximate nearest neighbor algorithms help to mitigate the conceptual cost. Algorithms utilizing the graph based approaches show the promise in enhancing the scalability. The continuous research is aimed at improving the efficiency of spectral clustering methods. You can see the graph shown over on the right side of an slide. It is a perception performance trademark. Up and to the right is better. The red shows anomaly. The red specifies the brute force. The yellow specifies the fascist, and blue specifies the ellipse. Conclusion in the future directions. A spectral clustering with a linear embedding offers a robust framework for discrete clustering in a large data scale. Ongoing advancement is conceptual techniques with the further enhance its applicability. Future directions may include the hybrid methods that integrate the spectral techniques with the deep learning. From here, I conclude. Thank you, one and all.